some of the details about what I do. Get a little slide. I'm hoping it'll keep you guys awake. I don't know how many of these presentations y'all have been to today. That was the first one, 4. Third one, lunchtime's coming up, man, so I better fly through these slides, I guess. I do have a little bit of show and tell. I'll kind of pass that around towards the end so you guys can take a look at what the end result is of some of the things that we do. Today we're going to cover a little bit about my background, what is electrical engineering, where it's used, some of the notable figures, the college coursework that's involved, what I actually do in my role, how we do our design process at Wireless Seismic. Then we'll get into a little bit of applications and we'll have some Q&A. And I'm not opposed to if somebody has a question about something that's in the slide, just go ahead and raise your hand up and ask me a question and I'll answer the best I can. I am an ITT graduate of class of 95. That got me into my engineering role. I started out as a technician. Went on to get my bachelor's degree in 2006. I had 19 years in the electronics industry. I spent 2 years in customer service and field service where I repaired seismic equipment as it came in from the field. I was actually deployed out on a seismic vessel to do some ocean model cable work where we went out and did exploration out in the Gulf of Mexico. I've got 13 years in engineering. I went from field service, customer service into the engineering. I became an engineering technician, and while I was a technician, I went back to school and got my engineering degree. I figured I wanted to do what the engineers could do. They had me designing stuff, so I wanted to finish that out. I spent 4 years in the computer industry. I was at Hewlett Packard from 2008 to 2012. I started out in data center control, which was really just kind of a different type of sensor application. I had been dealing with sensors in the seismic arena and then moved into data center control, where they controlled the air handlers that actually pushed the air around to keep the racks cool. Then I did server design. I designed the G7, Gen 8 server platforms, which I'll talk about a little bit later. And then I moved into program management, and that's where I kind of did my career at HP. What is electrical engineering? You can see it's a branch of engineering that deals with practical application of electricity, especially in power generation, related to communications and distribution of power, and design and operation of machinery. Where is it used? As just mentioned there in the definition, it's used in power applications. A lot of us, when we hear about electrical engineering, we think of the big substations where they generate all the power. Computers, oil and gas exploration, travel, airplanes, automobiles, all these things have got multiple processors in them that are controlling how the system works. Your smartphone, tablets, structural integrity monitoring. They'll go and they'll embed sensors into bridges so that they can monitor to see if there's any imperfections or possible catastrophic failures. And toys. We all like to play with our little video games. Electrical engineers, the ones that design those things. So some of the notable figures, a lot of these names may not mean much to you, but these guys were originally from the late 1700s and 1800s. James Clerk Maxwell, he came up with a set of equations where he went and worked with other engineers. He had taken some of their information, and they have lots of equations, and he boiled them down to about 4. And that's what is used primarily for our telecommunications industry today. It dealt with electromagnetic propagation and how you can actually send a radio wave. Michael Faraday, he dealt with electromagnetic fields. And he also came up with something that's called a Faraday cage. I don't know if any of you guys have seen a guy get into a big metal ball and the lightning strikes the ball and doesn't kill the man. That's a Faraday cage. Similar process is used whenever you have your radio transmitter, like in your phone. If you were to crack your phone open, over the transmitting section you'll see that there's a can. And that can is a Faraday cage. What it does is prevents the electromagnetic energy from radiating out except through the spot where the antenna is. Then we have Nicola, Tesla, and Thomas Edison. I was doing a little bit of research on these guys, and they lived at the same time. Thomas Edison was, of course, the inventor of the light bulb. That's what he's mainly known for. but he's also known for DC power transmission. So that's a non-alternating current. What we have coming out of the wall outlet is alternating current. And DC current is what Edison pushed. Well, Tesla worked for Edison, and they kind of had a falling out. Edison had some dynamos, which is basically a rotating magnetic field that produces energy. And Tesla said that he could fix it, and Edison said that he would give him $50,000 if he could do it. Well, that $50,000 back in 1920 was about $600,000. Well, Tesla went on and made it work, and then Edison said, no, I was just kidding. So, we really got to be careful about what we say. But Tesla won out in the end, because as you know, that we deal with AC transmission lines now. So the reason we use AC transmission lines is we can use transformers. So you can step up a voltage or step down a voltage. So if you look at these big substations, they're putting out like 300,000 volts. But what you get out of the wall outlet's only 120 volts. The reason they do that is they can increase the voltage and it decreases the current. The power would stay the same. Right? So if we've got 120 volts coming in at 20 amps, and we have 2,400 watts, basically, right? But we could have 300,000 volts, and very small current, and still have 2,400 volts. Some of the big designers in 1945, which are William Shockley, John Bardeen, and Morton Bottain, these guys invented the transistor. So we would be carrying, I don't know if you guys are familiar with the Sony Walkman and the big jumbo boxes, but they were transistorized, luckily, when I was a kid. But prior to that, they had vacuum tubes. They were glass tubes, some of them about this big, they were about that big around and bigger. And I couldn't imagine walking around, having my tubes in my pocket carrying big vacuum tubes. That was their accomplishment. And of course, we know Alexander Graham Bell, right, with the telephone, and sitting in the room, and he and Dr. Watson were in two separate rooms, and they plucked a string, and then they were actually able to start getting voice communication over a wire. And then we have William Shannon, Marconi, and Yagi. These were terms Shannon came up with. He is kind of known as the father of communication theory. So you're going to learn when you get into college that if you sample a system, you have to sample it at least twice as fast as the signal that you're trying to sample from, because you won't be able to fully reproduce that signal. We'll talk a little bit more about that in the Seismic application. Marconi and Yagi were antenna guys. They figured out how to design antennas and so that we could transmit signals. Joseph Fourier is not really an electrical engineer. He was more of a mechanical guy, and his original concepts dealt with chain links and heat transfer. But the funny thing about engineering is there's a lot of dualities. A lot of mechanical systems can be modeled as electrical systems and vice versa. So what many of the engineering systems use today is called Fourier Analysis. And what that does is it takes a time domain signal, which is basically anything that we would recognize, and it converts it into the frequency domain. So the frequency domain deals with harmonics. So you have 60 hertz, and then a first harmonic, or the second harmonic is 60 hertz, we get 120 hertz, and then 180 hertz. So this you can see whenever if you hear the term spectrum analyzer, you're actually looking at things in the frequency domain. And a lot of these I got from this Wikipedia site. So you guys, I'll leave the presentation with Derek, and you guys can take a look at it. And, if you're interested, go take a look at some of these guys. And there's a lot of really notable figures. These guys just kind of stuck out in my mind. Some of the coursework that's involved, of course, it's a lot of math. I didn't put any real math on here, but you've got 3 levels of calculus, you have differential equations, and that scares a lot of people, but it's fun. Engineers are problem solvers, and all math is a bunch of problems. In the DC circuit area, you learn about resistors, capacitors, and inductors. Those are the basic elements of electronics. So in AC circuits, you take that and then you apply what I mentioned with the frequency domain. You apply frequencies to it and you see how it behaves there. Electronics, you get into what's called diodes and operational amplifiers, where you can actually amplify signals and you can rectify signals, figure out how to make an amplifier. When I was at ITT Tech, we had to build an amplifier. It's a PA system that you spoke into a microphone and you came out to speak. Power electronics, we deal with MOSFETs and power FETs. You're dealing with these 300,000 volts. Digital signal processing is interesting. Our cell phones, right? Basically, you speak with an analog signal. It gets taken into the cell phone, and it gets processed by a digital signal processor, and it gets converted so it can be transmitted. You learn about signals and systems in those types of classes where, as I mentioned, there's calculus and differential equations. It all sounds difficult, but a gentleman by the name of Laplace found out a way to convert a differential equation into algebra so that just about anybody can do it. Electromagnetics, that's where you're dealing with transmission lines and transmission theory. Antennas, you learn how to design different antennas from, microwave antennas to GPS antennas. An antenna, as you see here, it's a 2.4 gigahertz antenna. In digital electronics, you learn about logic gates, right? What an AND gate is, what an OR gate is, exclusive OR gate. So all these terms are, just flow with the terms of logic design. Microprocessor theory. I don't know how many of you guys are interested in microprocessors. Anybody? Programming. You learn about the architecture. You learn about how to program them. You learn about the registers inside. Then you move into advanced logic design, where you take what you learned in your digital electronics course, and then you write software to emulate that. Then you get into motors and generators. So you've got AC and DC motors, and again, these power plants, they use generators to provide power to us. So what do I do at Wireless Seismic? I design high precision data acquisition systems for the oil and gas industry. I do troubleshooting on electronic design. I do data analysis. We'll get information back from the field, or our factory will have an issue, and documentation. Engineers do have to document things. We just don't throw stuff out there and see what was built, right? We have to put a plan together, and we have to put the requirements. What is this thing supposed to do, and how are we going to go and implement it? And I'm actually a manager, so I get to deal with people as well. So our design process at Wireless Seismic, we start with requirements. And basically it is what the customer wants, what new features are to be designed, and what problem is trying to be solved. So we'll get this information from our marketing team. They'll go out to different trade shows and they'll say, all right, we need this feature added. Our customer wants this. So what we do is we go back and we figure out how to do that. If we determine that it can be done, we'll write a definition. So that, how can we do this? Say they want this particular feature, but it can't be implemented the way they want. We can give them an alternative and then provide that solution. Then we have to know what it costs. Everything's not free, so for us to manufacture to make a profit, we have to actually look at what it costs to build it. Then we have to look at the technologies that are available. We run a 5 megabit radio in our system, right? But we need more bandwidth. So at the time we started this company, 5 megabit was it. So now we're looking at going to 16 megabit. So bigger and faster is what we're looking for. But we have to look at what technology is available at the time. So in the design process, we have electrical design, which we do research and simulation. We do component selection, schematic design, PCB design. And there's mechanical, right? You have to have somebody that actually builds these enclosures like I have here. So they have to design the top, the bottom. They design the tooling that actually makes it. It's a cast part. So they go in, they heat up aluminum, they inject it into a part, and then it cools, and this is what comes out. We have industrial design. Right? People that go in and they actually look at how things are used. Like this chair, why is it designed this way? Well, it's got a certain ergonomic feel to it, right? It doesn't feel very comfortable, I guess, if you've been in 4 of these things, right? But it's how it looks, how it's designed. This box, what interested me in this company is this box turns on by turning it up like this and turning it back. Right? If you think about guys out in the field, they've got big bulky gloves. They can't go push a little button, right? They tilt it, it turns on. They tilt it, it turns off. It's pretty insightful. Then you've got software, right? Somebody has to write the code. So there are firmware engineers that write the embedded code to make all this system work. After we've designed it, we've got it written on paper and put it out, then we actually build a prototype. Right? So we'll send out to a manufacturing house that build our PC boards, they'll populate it, and then they'll bring them back to us, the engineering team, and troubleshoot the boards to make sure that they're able to ship. If they don't, then we have to iterate. So we kind of go back to the beginning and start over. Okay, where did we mess this up? What can we make better? Then you have production. So there are electrical engineers that work in the production environment. They design systems, conveyor belts, control systems, manufacture manufacturing test. So you go in this box and the boards I've got, I'll show you, you plug them on a fixture and it automatically runs through a test. And you have people that do assembly. Sometimes there's automated assembly where there's no person touching it. You just stick it in a machine and build it. Then you go into distribution. So sorry these slides aren't very good. I was kind of expecting them to be not as good. But we do, in the part of our research phase, we do circuit simulation. Has anybody heard of a switch mode power supply, a switcher, a regulator? So the good thing about switch mode power supplies is they're efficient. And you remember what I talked about a little bit earlier about transformers. This switch mode power supply has got a transformer. So these things can operate at about 97% efficiency. So that means you're only losing 3% in heat. Sorry this didn't come out, but this is basically what we do is we look at the simulations and we can see this is a startup scenario. So if there were a spike out here, we know that there was a problem. But it starts up and regulates into steady state. So other things we look at are the output capacitors. This capacitor right here is what's called an output capacitor. And as I mentioned earlier about the frequency domain, we look at this in the frequency domain and we see that as we go down, we've got a hump here, we've got a hump here, and this is at 100 kilohertz, 200 kilohertz, 300 kilohertz. So we look at things like that and we say, well, can we make it better? So what we do is we take that, it was a 10 microfarad capacitor, we put a 50 microfarad capacitor in. Right, as you can see, this blip is smaller. What does that really mean to us, right? If these blips are big, we can interfere. So have you guys ever turned on the AM station in the car? Or is it all satellite radio now? Anyway, but you have an alternator in your car, right, that's generating power. It's a hump, right? Same thing here. You go in and you put a filter in to reduce that hump. We do other types of simulations too, other than just power supplies. This one is just a basic resistive network. We spent several weeks working through the math on this. We were having a problem in the field. And basically it boiled down to a component on the outside. And with simulation, we were able to go through and we could put in multiple values and we could see what the results were. After we got our circuit analysis done, we designed all this, we go into what's called schematic capture. And we put all of our circuits on the board, we draw all the connections, and then we move into PC layout. It's going to be difficult to see, but basically what it's doing is just pulling all the parts in and sticking them on this board. We design what the board size is, just pulling the parts in, putting them on the board. Then it's going to move into a section where it starts routing. And again, it's kind of difficult to see, but there are traces actually being put on the board where this gets routed. This is a two-layer board, so it doesn't have to do a whole lot. It's got two components on the back side and several components on the top side. And then the good thing about software these days is actually you can do 3D modeling as part of the software. You pull the parts in and put them on the board, and you can do slip them in your enclosure and see if it's actually going to interfere with something. That was a two-layer board. This is a 10-layer board. What we're kind of seeing here is a top-down view where we look through every layer of the board. Now, as an electrical engineer, we have to understand how PC boards are made. So I'm going to give kind of a quick overview. But all this gold color is actually copper. And what they do is they'll go in and they'll lay down what's called a photoresist. And basically that is just a mask that covers up this, and then they stick it in an acid bath, and it etches away all the rest of it. So all the black that you see here is copper that's missing. Now these boards are built in a stack, so it's got a layer of copper on the back, a layer of copper on the front, and then there's a material in between them. So when multi-layer boards, this would be the back side of that layer. So again, it gets a photoresist, and the only pieces that were cut out were what you see here in the black. Those were HESSC. And this is one of the inner layers. I just kind of wanted to show, what these regions look like separately. So, you might think to yourself, well, what happens? All this black is copper that's gone, right? So sometimes in the process, these boards can get warped depending on the size. So if they're small boards like we deal with, it's not so much of a big issue. But if you get into big boards like server motherboards, then the board can actually warp, and then it won't fit in the enclosure, or you can break parts off the board. So what the companies will do is they'll come in and they'll put copper pads on this so that they can prevent that warping. So now we get into a little bit of application. I'll tell you a little bit about what I've done. So at HP, I worked on a server system called the SL6500 series. And these servers were built in what's called rack unit sizes. So this one is a 1U, we have a 2U, and then this one takes up a full 4U. These particular designs were meant for high performance computing and hyperscale. And what that means is they sell these by the tens of thousands. Microsoft would come in and buy 40,000 of these at a time. They had to be efficient. We had to make sure that the power requirements were met for the amount of processing power they wanted to get out of it. Worked on the G7 version of this. I was an engineer on that product, and in 2010, Taitech University in Japan was number 4 on the top 500 supercomputer list. So that was a pretty neat deal. These particular servers are designed to handle graphics processing units. They're basically graphics cards that deal with complex matrix math. This unit here, the 250, could do 3 of them, and the 270 could do up to 8 of those cards. Did a lot of multiplexing, a lot of configuration. So with this rack, this chassis, you could actually fit 10 of them in a rack. And management is key as well. So now you've got 40,000 of these servers. How do I manage them all? So we designed a system called the SL Advanced Power Manager. And this is where marketing gets involved, because if you look at the acronym, SLAPM, who wants to slap them, right? But that's marketing for you. So, but this device would control up to 88 servers. So you can make it power control them, it would cycle power on them, and then you could also pull status. So the other thing I'm into is seismic data acquisition. And what this shows is basically what happens is you feed a source into the ground and the geophones receive the signal that comes back. So what are the components of this system? You have to have a sensor, you need an A to D converter, processor, telemetry, and storage. So a geophone's a transducer that converts motion energy into electrical energy. How many of you guys have seen those flashlights that when you vibrate them, they turn on the light, there's no batteries? Same concept. You have a magnet that moves inside of a coil. That magnet, let me ask this, how many of you have actually built the electromagnet with a nail and a wire? You ever done that? All right, so the same principle is, now you have a magnet moving through a wire, it produces an electric field, right? It produces a voltage. And then what we do is we measure that voltage. Now that voltage is proportional to the velocity. Why would that be important? So we go back to this picture, those signals come in the ground, and as you can see here, each one of these layers has a different velocity. So it's measuring the signals coming through those different layers of Earth, and it records that information. So we talk about analog to digital conversion. We have an analog signal that comes in, and you have a converter. It takes that analog signal and it digitizes it such that a processor can manipulate it. Some of the pitfalls, 8 million levels or more. We've got an A to D converter that's 32 bits, which gives us 4 million levels. 4 billion. So what happens when the data gets into the processor, right? We have to filter it. So it goes in, it runs through an algorithm, which actually takes out the unwanted tones. So we've got some of those harmonics that are there. We don't want them, so we can filter them out. It takes the data that we get, we've got to send it somewhere, so it puts it into a packet. Right? We have to know what the timing is. We've got a bunch of these things on the ground, and we have to sample them all at the same time when the data gets all mixed up. And then we have to control when we actually transmit the data. So telemetry, right? Telemetry deals with transmission of data. Right? We have to have certain protocols. And if we're transmitting over the air, we have to know what frequencies we can transmit in, or we get in trouble with the FCC. If you're transmitting over cable, you have to set it such that the cables don't get imbalanced, and you can't get a signal through. We have data compression, right? It takes all the bits and it effectively zips them up and it allows you for more effective transmission. And we've got bandwidth, right? How many signals can we put on a cable at one time or in the air? And there's also redundancy, right? What happens if my transmission doesn't make it? How do I get it back? And then storage. So we've got all this data coming in. How do we store it? So we have a recording system. And as you can see here, we get about 3 terabytes of data a day. And if they have a 90-day job, that's 270 terabytes of data they've got stored and then transmit. So seismic deployments, there's several different methods, but the 2 main ones are grid-based. And then there's, I don't know if you've heard of fracking, but what they do is they pump water into the ground and they shear the subsurface. And that's what this is. It's a frac star. So we actually crack the ground there, and then we measure out here the response. So on a seismic spread, it's laid out in a grid, as we showed before. And each of these units has a sensor on it, one of the geophones. These trucks actually shake the ground, and then the data goes back into the central recording truck. So there are many ways to do it. A lot of companies use dynamite. They have thumper trucks where they'll just have an impulse. There are places in the country where you can't use one of these trucks. You have to use a hammer. So you still plate on the ground and use a slate hammer. This is a vibrator truck, and it weighs about 65,000 pounds. They'll take 5 of them, and they'll stick them in one spot. They'll shake the air about 10 to 128 hertz, and all the signals get received by the geophone, and then they drive the trucks on to the next location. So what happens is the data comes back, right? So it's coming, and we've got, in the industry we call them wiggles, but each one of these is a geophone trace. And depending on, if you look at the amplitudes and you look at how close together they are, that tells you what type of structure it goes through. I don't really know what it goes through. Geophysicists know this type of stuff. This data gets sent to them and they process it, and then that tells them where they can go to drill a hole. So in the central recorder, they get a big picture, an overall picture. You have an observer, and what he does is he sits there and he measures this whole spread. These spreads can be 100 square miles. Right? So they'll go out in Saudi Arabia, or they'll go here in Texas, and they'll be in 100 square miles. They've got 4 large monitors that they monitor all this equipment on. And they run their diagnostic tests, and then it allows them to know whether it's okay to shoot. Now, our equipment has got to be able to go from Saudi Arabia, it's got to be able to go to Siberia, it's got to be able to go to downtown Dallas. So we have to design these things such that the components we use, the electrical components, can handle all those different temperature ranges. So basically we did a job in Dallas, and each one of these is stationed, and then there's a vibrator truck. It's a little smaller. We were having some issues with the crew. One of our guys out in the crew, one of our field service engineers, sent back some information, and he was showing us, all the global turmoil we're having with ISIS. This is a noise record where they're not acquiring any data, they're just sitting there looking at it come back. 40 miles away, there were some explosions going on due to ISIS. And this is the stuff that they picked up. So we have very, very sensitive sensors. So wireless seismic, I'm going to give you a little bit of information about it. It started in 2006. They designed a wireless system that behaves as a cable system. So we get all these out there. In the old days, back 15 years ago when I started, we were using cables. So you're 300 meters worth of cables between these boxes. Right? So that's a lot of copper. They got 6 twisted pair in them, and you've got to carry these things on your shoulders. So what wireless does is that we can build a better mousetrap, right? So we built a wireless system. We provide real-time data. There are systems out there that are called node-based systems. What they do is they fill them full of memory, SD cards basically, right? And then they go out there, they turn on the GPS, they start recording data, and then they shut off. The good news is it's very simple. The bad news is you don't know if you actually recorded any data in that memory until you take it back to the recording truck and pull it out. Our system, you can actually see it real time. As I mentioned, lower weight for the same number of channels. You guys will hear once you get into the industry about health, safety, and environmental. That's HESSC. Right? What environmental impact do we impose whenever we go in and lay out a bunch of cables or layout systems? So we have to minimize that impact so that when we leave, it's just as good as it was before we got there. So here's a little marketing fluff from our company. There's about 25 nodes here, and there's 25 nodes here, and as you can see, these 25, they fit in the back of the Gator. There they've got a flatbed. They've got all the cables, all the units, and all the batteries. So that's all I've got. Did a lot of talking. Any questions, guys? Yes, sir.
What is the main use for urban seismic measurement?
It's oil and gas as well. They're looking for deposits. Some, the county may own some mineral rights. They want to know kind of what's going on. So they'll do it there. Make sense? It could. It could. And as you notice, in this application, they were using a smaller version of the battery. I've heard stories from some of our field service guys who were working in Dubai where they actually ruptured and went through the ground into the sewer pipe. So, it's not good. But a lot of them will use metal plates. I know when they were doing some stuff out in San Antonio near the Alamo, they had a big plate. They were swinging a sledgehammer. So what I'm going to do is I'm going to pass around a few things for you guys to look at. There's no problems with y'all touching these, but what we did, let me just give a little background. So when we originally designed this system, it was all modular. All right, so pull them apart, but that's not cost effective. As I mentioned, cost before, right? It's key. So each one of these boards has to run through on its own. Right? They'll build them in a panel, but they'll be separate panels. So what we did is we took and put those three boards onto this one board. So I'll pass around a couple of sets. You guys take a look.